Chemistry is the science governing the physical properties of matter and the tangible macroscopic transformations of the universe. We define matter by its physical behavior. Solids hold a fixed shape, liquids conform to their container, and gases fill the available space. Our perception is largely trapped within this macroscopic domain. We treat a solid block of metal or a pane of glass as a permanent object, but treating matter as static is a perceptual illusion. You cannot understand the forest without uncovering the invisible, frantic behavior of the trees. To find the source of these properties, we have to descend past the solid surface of everyday matter and into the microscopic domain of atoms. The classical model describes this space as a central nucleus surrounded by a cloud of electrons. The traditional visualization of these electrons traveling in fixed circular tracks, like planets orbiting a sun, is entirely incorrect. The planetary model is dismantled by a single law, the Heisenberg uncertainty principle. This principle dictates that it is physically impossible to measure both the precise location and the momentum of an electron at the exact same time. Without knowing both where an electron is and where it is going next, plotting a defined orbital track becomes a mathematical impossibility. Physical reality is not governed by predictable clockwork tracks, but by unpredictable probabilities. These probabilities take the form of atomic orbitals, three-dimensional regions of space where an electron is most likely found. A baseline s orbital forms a symmetrical, spherical probability cloud. The p orbital shapes this field into two identical balloon-like lobes tied at the center. Electrons populate these levels, starting closest to the nucleus before expanding into distant shells. These mathematical probability clouds dictate the structural boundaries and physical limits of every element. Most elements possess unstable, partially filled outermost orbitals. This creates a thermodynamic drive to interact and bond with neighboring atoms. In ionic bonding, a nonmetal steals an electron from a metal, locking them together via opposing electrical charges. In covalent bonding, two nonmetals mutually share electron pairs, overlapping their fields to mathematically complete their outer probability shells. The macroscopic properties of all solid materials are the result of billions of atoms ruthlessly seeking orbital stability through these bonds. For matter to actually transform, particles must physically crash into each other, but merely bumping into one another is not enough. The vast majority of atomic collisions fail to trigger a reaction. To succeed, reacting molecules must strike each other with exact geometric orientation. They must collide with a minimum threshold of force known as activation energy. Raising the temperature forces molecules to move faster, increasing the violence of these collisions. Increasing concentration packs more molecules together, multiplying the frequency of high-energy impacts. Chemical transformation is never a guaranteed, orderly event, but a chaotic, high-stakes kinetic lottery. Chemical reactions rarely run to a state of completion and then permanently stop. Instead, they reach dynamic equilibrium, a state where the forward reaction and the reverse reaction occur at the exact same rate. While the system appears completely frozen macroscopically, it is actually a frantic, perfectly balanced two-way microscopic exchange of atoms. If this balance is stressed by a change in pressure or temperature, the system automatically shifts its reaction rates to counteract that stress. From the unpredictable probability of an electron to the shifting kinetic balance of reactions, reality is an endless, dynamic dance seeking stability. It is the most recognizable symbol in all of science, a tight central nucleus surrounded by perfectly orbiting electrons. It looks like a miniature solar system. We see it on textbooks, corporate logos, and television graphics. This mechanical layout was championed by physicist Niels Bohr. His model offered a predictable universe. If you know an object's speed and its exact position, you can map its entire path, whether that is a planet circling a star or an electron circling a nucleus. But in the subatomic world, this mechanical model fails. The physics that govern planets do not apply to the scale of the atom. The physicist who proved this was Werner Heisenberg. Heisenberg's uncertainty principle established a strict boundary on what we can observe. On a subatomic scale, you cannot simultaneously know an electron's precise position and its momentum. If you measure its speed with total accuracy, its exact location blurs out into a haze. If you pin down its location, its speed becomes a mystery. Because an electron's next move is permanently unknowable, we cannot plot a planetary track for it. The predictable rings disappear, leaving a void in our understanding of how matter is actually organized. To rebuild our model of the atom, we start at the absolute center, a dense nucleus made of protons, which determine the element's identity, and neutrons, which provide its mass. The space around that nucleus is not composed of empty rings. Instead, the electron occupies a three-dimensional probability cloud, known as an atomic orbital. An orbital is a mathematically defined region of space. When we plot out an orbital, we map the territory where there is a 95% chance of finding a specific electron at any given moment. The foundational s orbital is a hollow sphere around the nucleus. Next, a larger, diffuse 2s orbital forms outside it. Inside this second tier, probability dots cluster toward the center. 2s electrons penetrate inward, spending time close to the nucleus, lowering their overall energy. By shifting away from predictable tracks and plotting these probabilistic territories, chemistry moves from a study of mechanics to an exercise in statistical geometry. At the second energy level, electrons begin to inhabit a more complex geometry, the p orbitals. A p orbital resembles two identical balloons tied at the nucleus. They appear in sets of three, pointing outward along the x, y, and z axes at right angles. Between the top and bottom lobes sits a flat horizontal space called the nodal plane. To understand why this plane matters, we have to view the electron as a wave. Just as a vibrating string has a stationary point where there is no motion, the electron wave has a node, a place where its probability of existing is exactly zero. The electron exists on both sides of this divide, but the math of its wave nature means it is never found on the plane itself. As elements get heavier, the spatial arrangements grow even more intricate. The atom begins organizing electrons into multi-lobed structures known as d and f orbitals. The subatomic landscape is not a set of empty rings, but a dense, overlapping architecture defined by these mathematical constraints. Nature does not scatter electrons randomly into these clouds. They populate the available space by following a strict sequence, summarized by the Aufbau principle. This diagram shows orbital rooms holding up to two opposite spinning electrons. By the Aufbau principle, electrons fill lowest energy spaces first, 1s, 2s, then p. Because 4s sits below 3d, it fills first. Per Hund's rule, electrons occupy equal energy rooms singly before pairing. These rules of capacity and energy take an otherwise chaotic cloud of probability and organize it into a predictable hierarchy. When we discard the mechanical rings, we replace them with shifting geometries. When atoms meet, these probability clouds overlap and merge to create physical bonds. This distinction matters because the specific stacking rules of these orbitals dictate the chemical properties of every element. Whether there's the structure of a carbon atom forming a diamond or oxygen binding to iron in the bloodstream, the precise overlap of s, p, d, and f orbitals is the mechanism that holds matter together. The universe is not built on rigid deterministic tracks, but on these fluid regions of probability. By shifting our focus from where an electron is to where it is likely to be, we replace the mechanical fiction of orbits with a statistical map of how matter is constructed. Look around the universe, and you will see matter in a constant state of turmoil. Iron rusts, wood burns, and elements violently collide. But sitting at the far right edge of the periodic table is a group of elements completely detached from this chaos. The noble gases, like neon and argon, remain entirely pristine and unreactive. They exist in a state of absolute, untouchable energetic stability. They require nothing from their environment, and they concede nothing to it. The burning, rusting, and explosive reactions we observe every day are simply the rest of the universe trying to achieve that exact same state of perfection. This diagram shows a cross-section of a noble gas atom. The key feature is this outermost boundary, known as the valence shell. Maximum stability is achieved when this valence shell contains exactly 8 electrons. This structural requirement is known as the octet rule. The vast majority of elements do not naturally possess 8 valence electrons. They have incomplete outer shells, leaving them highly unstable. To resolve this deficit, atoms are forced to interact. They must trade, share, or pool outer electrons with neighboring atoms to reach that required number. Chemistry is an entirely predictable, universe-wide drive for elements to build a complete 8-electron valence shell. We generally view the periodic table as a flat list. In reality, it operates as a precise topological map governed by strict physical laws. An atom's exact coordinates on this map dictate its physical properties and how it will interact with anything it encounters. This layout isolates a single vertical column, or group. Every element here holds the exact same number of valence electrons. Because these layouts match, they act as chemical siblings with similar reaction patterns. Their chemical destiny is completely predictable. Every atom is locked in an invisible internal tug-of-war. The positively charged nucleus pulls inward, while the negatively charged electrons repel outward. Moving left to right across a period adds protons. This increases the inward pull, shrinking the atomic radius. Now observe ionization energy, the effort required to steal an electron. It spikes sharply as the radius shrinks and the core tightens. Moving down a column adds new orbital layers, causing the atom to swell. These inner layers act as a physical shield, blocking the nucleus's inward pull. Consequently, outer electrons are loosely held, and the energy to strip them away plunges. An atom's physical size and its grip on its own electrons are direct mathematical consequences of its coordinates on the map. To anticipate how two elements will behave during the collision, we measure their electronegativity, a metric defining an atom's hunger to acquire new electrons. This map shows electronegativity. The heat signature peaks top right, where small atoms have concentrated nuclear pull. Bottom left, the signature runs cold. Massive, shielded atoms exert almost zero pull. Comparing colliding atoms reveals how they achieve the octet. When two elements with severely mismatched sizes and properties collide, the interaction is violent. This results in ionic bonding. It occurs when elements from completely opposite sides of the map cross paths. The severe difference in electronegativity allows the smaller, hungrier nonmetal to completely strip an electron from the larger atom. The resulting magnetic attraction locks both into a rigid geometric lattice. A completely different mechanism plays out when two neighboring elements from the highly electronegative right side of the map collide. This leads to covalent bonding. Because their electron hunger is closely matched, neither atom has the strength to completely steal from the other. Instead, they compromise. They overlap their outer boundaries and share pairs of electrons to artificially complete their octets. The geographic distance between elements on the periodic map directly dictates whether their bond is a permanent theft or a shared overlap. Finally, looking to the far left side of the map, we find elements with extremely low electronegativities interacting with each other. This creates metallic bonding. Since these atoms lack the pull to hold on to their valence electrons, they simply release them. The resulting architecture is a grid of positive atomic cores, completely submerged in a highly mobile, delocalized sea of electrons. That mobile sea of electrons directly translates to macroscopic properties, granting metals their ability to conduct heat and electricity so efficiently. The tangible materials that build our world are simply the result of individual atoms following their exact geographic rules to find stability. Compare the way iron oxygenates over a decade to the way a flame consumes fuel in a fraction of a second. One process is a slow, methodical decay. The other is a near instantaneous release of energy. While their timelines appear fundamentally different, both events are governed by the same set of mechanical laws. This is the field of chemical kinetics, the study of reaction rates and the specific variables that dictate how fast a substance transforms. To understand why a reaction takes a year or a millisecond, we have to look at the precise moment two individual molecules interact. This reveals that the duration of a chemical event is a physical variable, dictated by the frequency and effectiveness of atomic interactions. On a microscopic level, A chemical environment is a space of constant, random motion, where molecules are perpetually ricocheting off one another. Collision theory states that for a reaction to occur, the first requirement is a direct physical strike between particles. Absolutely no contact between them means no transformation. But contact alone isn't enough. Particles must strike with sufficient activation energy, the kinetic force required to shatter their existing bonds. Even with enough force, particles must align at a precise interlocking angle to successfully form new connections. If the molecules hit with too little force or at the wrong angle, they simply deflect off each other, remaining chemically unchanged. Because these three criteria, contact, energy, and alignment, must happen simultaneously, a successful chemical reaction is a relatively rare event. This chart plots the energy required for a collision to progress from a reactant to a finished product. The rising line represents the activation energy barrier, the minimum threshold that a collision must clear. At the very peak of this curve is the transition state. This is an unstable, high-energy moment where the old molecular bonds have broken, but the new ones haven't quite finished forming. Some complex transformations might pause at temporary energy valleys along this path, creating short-lived intermediate substances before the reaction completes. Every chemical change is effectively a mechanical struggle to overcome this invisible energy barrier. By understanding these microscopic rules, we can manipulate physical environments to change the rate of these collisions in bulk. Crushing a solid increases its surface area, exposing a much higher number of particles to potential strikes. Increasing the concentration of a substance crowds the molecules together, which mathematically raises the probability of a physical collision. Raising the temperature increases the speed of the particles, leading to more frequent collisions and providing the extra force needed to cross the activation threshold. Catalysts are the most efficient way to manipulate the system. Instead of adding more heat or pressure, they provide an entirely different chemical pathway. This new pathway has a drastically lower activation barrier, allowing the reaction to proceed much faster without requiring more energy. Since the catalyst itself isn't consumed in the reaction, a single functional unit can facilitate millions of these chemical transformations. Adjusting these specific variables turns chemical reactions from random occurrences into highly controlled engineered events. These kinetic principles dictate the behavior of the macroscopic world we live in. Refrigeration is a deliberate attempt to lower the kinetic temperature of food, slowing down the molecular collisions that lead to spoilage. In contrast, industrial smelting uses extreme heat and increased surface area to force metals through rapid chemical transformations. Chemical kinetics serves as the link between the behavior of individual atoms and the bulk properties of matter we see every day. Mastering the mechanics of a single microscopic collision gives us the ability to control the exact rate of chemical change. Look at this sealed flask. From the outside, the chemical reaction inside appears completely finished. The color is static and the liquid is perfectly still. Underneath the surface of this motionless liquid, matter is in a state of constant, chaotic motion. Understanding the difference between this apparent calm and the actual behavior of atoms is the foundation for manipulating matter. Microscopically, reactant particles constantly fuse to form new product molecules. These products instantly tear apart, reverting to reactants. Eventually, forward collision rates exactly match reverse breakdowns. This precise dynamic equilibrium locks the overall amounts in place, giving the appearance of a silent flask. True chemical balance in a closed system isn't a state of rest, but a state of furious, perfectly matched opposing forces. In the late 19th century, chemist Henry Louis Le Chatelier codified how these systems behave under stress. His principle dictates that if an external stress is applied, the system automatically shifts its position to absorb the blow and restore balance. Let's test this by manipulating concentration. We inject a massive excess of raw reactants into our balanced system. Overwhelmed, it shifts right, accelerating the forward reaction to churn out more products. Siphoning off this new product forces the reaction to run indefinitely. By manipulating concentration, humans can prevent nature from resting, forcing a system to endlessly produce a desired material. Our second stress test relies on pressure. This specific vulnerability only applies when chemical reactions involve gases. We crush the container down with a piston. The volume shrinks, forcing gas molecules into a smaller space and causing internal pressure to spike. To survive, the cramed particles combine into fewer, larger molecules, reducing the physical crowding. Fewer total molecules bumping against the walls means less outward force. This lowers the internal pressure, restoring harmony to the constrained space. A chemical system will literally alter its physical molecular footprint to survive being crushed by its environment. Our third test treats heat as a physical participant. In an exothermic reaction, heat is generated as a literal product of the reaction itself. If we apply an intense external heat source to a system that is already exothermic, we cause a severe disruption. In this visual equation, the system treats extra heat as an excess product. Adding heat blocks tips the scale backwards, a shift left. The system absorbs the thermal energy, breaking products back down into raw reactants to cool itself off. Temperature dictates the direction of the reaction. Fighting a system's natural thermal output forces it to reverse its own creation. But what happens if a powerful chemical catalyst is dropped into the system? There is absolutely no shift in the position of equilibrium. This graph shows why. A catalyst speeds up both the forward and reverse reactions equally. The lines spike simultaneously, meaning the system just hits the equilibrium line in a fraction of the usual time. The system reaches the same endpoint it always would. It simply arrives there sooner. Returning to the macroscopic view of our sealed flask, we can now see it for what it truly is, a highly responsive engine. Nature abhors an imbalance and will always fight to counteract a disruption to its equilibrium. But humanity is no longer a passive observer of this phenomenon. We actively weaponize it. Industrial chemical engineers intentionally stress these systems on a massive scale. By carefully tweaking the pressure, continuously siphoning products, and tightly controlling the temperature, they hack the natural limits of the reaction. By mastering Le Chatelier's principle, we force the unwavering rules of nature to yield the materials, refine the fuels, and synthesize the medicines that sustain the modern world.